Fine. So Unit 4 Lesson 1, Bivariate Analysis is concerned with relationship between pairs of variables. Pairs of variables, there are two variables. So univariate has only one variable. In the last chapter we saw it was time or the marks or whatever that was, you remember?
Number of ticket.
And frequency. Frequency is not a variable, remember. Frequency is a number. Huh?
Of that
Of
one
that.
given
So don't take frequency as a variable.
Here you two different variables.
Yeah, you have two different variables over here. Correct? In a set of data. So sampling unit, so adult males, height, univariate. Correct? So variable is height. Adult males, if you look at weight, univariate.
What do you mean univariate?
Uni means one. One variable.
Yeah,
so one variable is called univariate.
Oh, right, okay. And then if it's both, then it's
if there are two variables together, then it's called bivariate. We will look for association between the two sets of data. So if you're looking at height and weight, what is the association between them?
Also.
Representing relationships as an equation. Can we get an equation for this?
Yeah, it's like a BMI.
Use a scale to describe the strength of the relationship. So what is the strength of the relationship? This is what we will be doing. Scatter diagram or scatter plot. These are the graphs used to investigate the possible relationship between two variables that both relate to the same event. Yeah. The relationship between two variables is called correlation. So what is the relationship between two variables?
Yeah.
The independent variable should be on the horizontal axis and a dependent variable on the vertical axis. Yeah. Yes. Positive correlation. Y dependent decreases as X increases or decreases.
Yeah. Directly proportional.
Negative correlation
is inversely proportional.
Yeah, when one increases, the other decreases.
Vice versa.
Yeah, so technically we don't call it proportional.
This is all stuff we know.
You know it very good. So here, if you see this is positive correlation.
Yeah.
Because as your one value, X is increasing, Y is also increasing.
Yeah.
This is a negative correlation.
And one's increasing, the other also decreasing.
This is absence of correlation.
It's like just random. Because some are increasing, some are decreasing, some are decreasing, some are decreasing.
Yeah, random. It's very random. Here, this is positive correlation.
Yeah.
Here, this is also positive correlation.
Over here, it's
so there's a weak positive correlation.
It's there,
some there, this is weak. In the last one, it's a weak.
So do you consider something a weak one when most of them increase?
The points are not clustered around a line.
Okay.
So if the points are clustered around a line, we say strong correlation. Like suppose if you draw a line. Now this is very strongly clustered, but it's negative correlation.
So strong negative.
Strong negative, yeah. This is strong positive.
And that's
this is weak positive. No, and this is even weaker than that.
Yeah.
So
and
this is weakest correlation.
Like no correlation.
Absence of correlation. There's no line you can draw downwards or upwards. Okay. Not all relationships are linear. So you have to learn only linear correlations.
Okay.
This is not linear. You can draw a curve like this. This is non-linear relationship with variables. Okay. The correlation between two data sets does not necessarily mean that one causes the other. The causation. So it's called a causation.
Yes, correlation. This is not causation.
This is not causation. Correct.
Correct.
You have done in psychology?
Just
very
now.
Good. Very good. That's a good thing. The bell tower Pisa Cathedral was built in 1178 and soon began leaning on one side, hence the name. The measurement below shows the lean in tenths of a millimeter. How much it is lean? Correct? Beyond 2.9 meters. So in 1975, the tower was leaning 2.9742 from the vertical.
Okay.
So amount of lean is given you. So here this is there. So if you have, this is a vertical. So the tower is like this. So how much is it leaning? How much is it leaning?
Okay, like the angle.
Not the angle, the measurement. This measure. It's not the angle, it's in meters.
Oh, the distance from the
vertical. So lean, so that's your lean. Correct? They've given you this data. Draw a scatter plot and comment on the correlation. Now, how do you do this on your calculator?
Okay. But you only have one variable, so it's what's it called?
Now, what you need to do in this case is, okay, or let me put it this way. Forget the calculator for time being. Let's do it by hand first to understand. So when you're drawing We'll draw the axis. Correct. Here will be your x-axis, and your lean will be your. What is the minimum year?
642.
1975.
Oh, so you make it years, yeah.
Correct. I'm just putting in 1980.
Yeah.
And 1990. Quickly, I'm just putting this. What is the minimum lean angle?
642.
So you put a thing like this.
So you're just approximating that, okay, over there.
640, 642. How much is it? What is the maximum? 760.
757.
7. So let's call this 600. Correct?
What just happened?
Okay, fine. Okay, fine. I was have touched something accidentally.
Yes. So basically, you put the 640. You think that in 60s or something.
So I was saying you put it 600 if you want. So that will be easy for you to plot, or easy for you to.
But why are you not taking 642 specifically? You're taking in tens or.
Huh?
You're taking it if you're not taking 642 specifically.
Yeah, you can take it tens. I don't have a graph paper here, so I'm just putting it like this. Chalo, 760. Correct. So then you can, you can just put those, whatever that is. So you can take, if you want to take them in 20s, so 660, 680, correct? 700, 720, 740 and 760. Chalo, take it. Fine. Now you mark it. So 1975.
It is 642. So
642.
Yeah. 1976.
644. 656.
Yeah. 667.
667, so it went higher than that.
Little high.
673 even went little higher. Correct? 688.
A positive, strong positive correlation.
Correct. 688, 696, and so on. Means it's a
strong
strong
positive.
That's what you. Okay.
Yeah, and it says comment on the thing, so it's strong positive.
Yeah. Line of best fit.
Yes, you can have data points outside, but whatever, I know what it is. It's like
yeah, correct. Okay, so you have a data point. You have draw the regression line, and you have to do using a calculator.
The regression line is what? Like
the line that you draw. Suppose you want to draw a line that models this data.
Right.
So you draw a line of best fit using your calculator.
So line of best fit is a regression line.
Is your regression line. Line of best fit is your regression line.
Also called,
Yeah. A line of best fit is drawn on the scatter diagram to find a direction of association between the two variables that shows the trend. The line of best fit is used to make predictions. So what is the use of the line of best fit?
Make predictions.
To make predictions. Correct? One method to draw is by eye. Now this won't be very accurate. It will be very subjective. Some people will say this is the line of best fit. Some will say that is the line of best fit. Yeah. Try to balance the number of points below the line and above the line. You have to balance.
Okay.
And include the reference point. This is very important. The reference point should be the mean values of x and y should always lie on the line.
So on your calculator, is there one way you just click it and it shows line of best fit? Or you have to find the mean first, then mark it and do it?
You have to find it will show you everything. Now let's do this for the leaning tower PISA. Let's get that. So what you have to do is you go to statistics, delete whatever you have. First of all, because we keep it clear always. Enter the first in column 1.
Okay.
Enter the second in column 2, obviously.
So this first is
Achha, sorry, I forgot. You may not put in 75, 76, 77 and all that. You make it a small number. So you can call 75 as 1.
Okay.
Are you following that? 1. So that you get an easy model. 2, 3, then 4. It's an order, no?
Yeah, it's an order.
There's no number. There's no year which is skipped, no? 5. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay?
Yeah.
6, 7, 8, 8, then 9, 10, 11, 12, 13.
So
and what will you write? What's your x?
What do you mean?
Your x is the number of years from
Yeah.
1974.
Yeah.
X is the number of years from 1974 because we have taken this is 1.
Yeah.
So from 74 this is 1 year.
Oh, why do you need to show x and answer?
1, 2, you have to show that so it becomes easier for you to model. You can't put these big numbers in your.
Oh, we say 1, 2, 3 means 1 year from another year.
1 year from 1974.
From,
2 years from 1974.
So it's your 0.
Huh?
It's like your 0.
Yeah. You can also call it 0 if you want. But 1974 is 0.
Fine.
Okay, now put the lean angle.
Okay, so 642, 644, 656, 667, 673.
You enter all those values. I'm just entering it.
Yeah, same. I've done that. I'm waiting.
Good, very good. You're faster than me.
It's harder on this.
757. Okay, fine.
Yeah.
Once you do this, now Casio doesn't know what is this and what is this.
Oh, okay. So you have to go to
Casio
set.
doesn't know. Yes, you have to go to set. So if this is there, so you exit, or go right here. Okay.
I think it's happening for me.
Go right.
I'm going right.
That's it. Now what you do is go to calc. F2 calc. Set. Now set is what you're telling the calculator. So you are now doing two variable statistics. So you'll come here. Two variable x list. Is a x list in list 1?
Yeah.
And your y list is the list 2. Just check that. If it's there, then
but,
don't
I don't know why it's showing this. This is matter.
One variable y x doesn't matter. The top thing doesn't matter. We are doing two variables. We are doing two variable statistics. So you look at that. That's your one variable. That's your earlier chapter.
And you get two variables.
Exit.
Two variables.
Listen to me. Don't jump. Don't jump to conclusions. Press regression. Press regression. Yeah. Press x. Press ax plus b. And that's your regression line.
Oh, so you plug it in substitute.
So y is equal to
9.32 x.
9 yeah, correct. Round it off correct to 3 significant x.
Good, okay. Plus 6 to 8. But if here, should we take more 6
to 8? No, but when you're writing your answer, you write it like this. But if you're using this further for further calculation, then take more. Okay, so that's your regression equation of what?
Of the number of years.
Of y on x. This is called the regression equation of y on x. Regression equation of y. That's your model.
No, I know, but what is it modeling exactly?
It's modeling the years with the years from 1974 with the lean angle. Okay. You know?
Yeah. So
years from 1974 to the lean angle it's modeling.
Yeah.
You followed this? Now R, you can see this R, 0.994. Your small r, what is the small r called?
No. I know.
Yeah.
Regression.
Carl Pearson product moment correlation coefficient. So it tells you the degree. So they'll call it, sometimes they call it the correlation coefficient. Okay. Sometimes they simply call it correlation coefficient, but don't get confused with that. Sometimes they'll write the entire thing. So the correlation coefficient tells you the measure. So now 0.0994, now a strong positive correlation would be 1. Okay. So the closer the value to 1, the stronger, the higher the correlation.
Whether it's positive or negative.
Negative. So negative one will be closer to -1.
Oh, so this is a strong positive.
There's a strong positive correlation.
So for a strong positive correlation, it to be closer to 1 or 1, of course. And
1 is perfect positive.
Perfect. Closest to 1. And for perfect and a strong negative correlation to be closer
-1.
close to negative.
Okay. So basically your R, the product moment correlation coefficient takes values between -1 and 1. It doesn't take any value beyond that. So that will come, I think, so subsequently. Okay, use a line of best fit to predict the data within the range is called interpolation.
Yeah, hold on.
What is interpolation?
I don't know.
So see, now this is very important. Look, the highest and the lowest value are called the poles.
Okay.
So this is the lower pole. Lower pole. This is called the upper pole. So what's your lower pole? 1975.
Oh yeah. Okay. So
What is the upper pole? 1987, not 1987.
Yeah. So for lower and upper, you see the x values.
The x values. Now, if you want to find out, listen, if you want to find out the lean somewhere in middle of 78.
Okay.
So then you go from 78 and find out the lean.
Yeah.
Correct? Yeah. That's called interpolation. So if your x lies between the lower pole and the upper pole, that's called interpolation. It's between that. Achha, if it lies beyond this, suppose if I ask you, what is the lean in 1990?
I approximate.
No, you can't do that. It won't be accurate.
Okay,
so that's called extrapolation if it goes outside the number. So using the line of best fit to predict a value within the range of data, between the poles, within the range of data is called interpolation. Okay. If the value is outside the data range, the method is called extrapolation. Interpolation is generally more reliable than extrapolation. Yeah. So extrapolation is not reliable. Okay. Because the tau may have fallen and you're doing the data using the line. So understand the regression line. Be careful when you interpret the regression line. The gradient of the line of best fit is the amount by which y increases when x increases by 1 unit. Oh. When x increases by 1 unit. The y-intercept might not always have a meaning. So in this case, if I ask you what is this, explain in context of the problem.
That's the slope, which means when y changes, no, when x changes, when y changes, x changes by 1 unit, something like that.
So there's a slope, that's right. Means you can say the lean will increase by 9.32
each time
meters
the year
for every
year.
Every year that time increases.
Because over here the unit is years, right?
Time increases.
So 1 unit increases.
From 1974, because we have taken 1974 as a base year now. To make it 1, 2, 3 year, this is what it means. Correct? What is 628?
Your y-intercept.
Y-intercept. So y-intercept will be the initial lean. So in 1974 the lean is 628. But that will become extrapolation anyway. But I'm just giving an example.
Did they ever ask
so that gives you the lean when the time is 0.
Did they ever ask you to find the lean of the
interpretation? Yes.
No, of 1974, of the 0.
They can ask and they say comment on it. So you can say the extrapolation, therefore it's not accurate.
But it can't be that.
It's not 11.
You can say that it's that, like it could be that.
Yeah. Try this now, let's see.
Okay. A study was done to investigate. Axis and the time taken to run.
So see, so data from the children age to 7 can interpret this. That study was done to investigate the relationship between what? Between the age is x.
Yeah.
And the time in minutes for which the child can run 1 kilometer. These are my two variables.
Yeah, when I say y did already tell you the axis is.
So y is equal to 20, yes, minus half x.
Yes, so if you are interpreting the slope, the
So-
slope is negative half.
So what is meaning of that?
I'm telling you, the time minutes in which the child can run 1 kilometer decreases by half with a 1 year increase in age.
Correct. Very good. X is the years, x years, and this is the time. So it's a negative correlation.
Yeah.
So while with every year increase, the time decreases. Correct?
By
To run 1 kilometer
Correct.
by half.
Yeah, yeah. And the y-intercept here is 20.
So y-intercept is 20.
Your initial, when the kid is 7,
Yeah, very good.
then the time that they take to run the 1 kilometer is 20.
20 whatever minutes. 20 minutes, yeah.
20 minutes.
1 kilometer, no? How can you run 1 kilometer?
I think 20 minutes.
Okay. Now this is positive correlation.
Earlier,